Hi, I'm Lawrence Krauss. Science matters, which is why I want to supplement our Regular Origins podcasts with a series of shows that regularly describe recent discoveries in science that are in the news. Not just to give perspective on what's happening, but also to celebrate some of those amazing discoveries that humans are involved in. I want to discuss discoveries at the far ends of the universe and ones that are much closer to home. And I want to begin today, in fact, with one of those discoveries that is right in our neighborhood. In fact, I want to show this device right here, which may look very strange, but it's a device to discover the lifetime of a neutron. Now that itself is remarkable because neutrons are the most abundant particles on Earth. Most of the atoms in our body contain more neutrons than protons. Nothing should be more familiar than neutrons, and the fact is neutrons are radioactive, which is very strange. If I put a neutron here in empty space, it will decay in about 14.5 minutes. But we're mostly made up of neutrons. How can that be? It's a remarkable property of physics and nature that neutrons are unstable when they're out in empty space or on their own, but when you drop them in an atomic nucleus, they become stable. Remarkable. It's a fact that has helped us understand the properties not just of nuclei, but of elementary particles themselves. But trying to understand the lifetime of a neutron is very important, not just for fundamental physics purposes, but also for cosmic purposes. For example, understanding the lifetime of a neutron helps us better understand why the universe has the amount of helium it has today compared to hydrogen. So we want to try and measure the lifetime of the neutron as accurately as we can. And we've come a long way in the last 40 years. You'd think, after all, with the most abundant particles on Earth, we'd know the lifetime of the neutron as well as we know anything. But there's a mystery and a puzzle. When we measure the lifetime of the neutron, we can do it two different ways, and each different way gives a different lifetime. One of the ways to measure the lifetime of a neutron is to basically put neutrons into something called a neutron bottle, where they just sit there and you count the number of neutrons in that bottle over time, see how quickly they disappear, and that gives us the lifetime of the neutron. When you do that, you find out the half-life of a neutron is about 14 minutes and 39 seconds. But another way involves a device like this. Neutrons decay into protons, electrons, and neutrinos. Now, if I shoot neutrons in one end of this device, I can measure how many protons come out the other end, and that will tell us how many neutrons have decayed. And when we use that technique, we come up with a lifetime that's 8 seconds longer. Now, 8 seconds may not seem like a lot, but the experiments are so precise that the difference between those two lifetimes is something called a 4 sigma difference, which should happen randomly only about 1 in every 10,000 times you do the experiment. Unless, of course, there are systematic errors that we haven't taken into account in doing the experiment. So experimenters at the National Institutes of Science and Technology are building new devices like this to try and perform the experiment better to see if there's some experimental flaw that's giving that difference. But maybe it isn't an experimental flaw. Maybe it's a fundamental property of nature. And theorists have jumped on the bandwagon and begun to discuss how could you make these two different experiments consistent. Well, one possibility that's been proposed is that neutrons decay every now and then, not just into protons, electrons, and neutrinos, but into other particles, perhaps particles that aren't detected in an experiment like this, particles that zip right out without being detected, particles that might form the dark matter that makes up most of the mass of the universe, our galaxy and the universe. Now, those particles would have to have a very particular property, and if the neutron decayed into those maybe 1% of the time, you could resolve the difference between those two experiments, because when the neutrons decay into other particles, they won't be seen as protons coming out, and it will effectively make it seem like the neutron lasts longer by potentially 8 seconds. Now, this is controversial and very speculative, and there are already constraints ruling out many properties of this potential dark matter if it's there. But what I find amazing is that this tabletop experiment in a room you could do here on Earth with the most abundant particle on Earth, something we should know something more about than anything else, might lead to an understanding of a mystery at the forefront of science. It's actually so fascinating that I'm actually thinking about right now another possible explanation of this. It is remarkable that there are puzzles and mysteries to be discovered, not just way out there in the cosmos, but right under our noses. So that's the first thing I wanted to talk about, really close to home. But there are a bunch of other mysteries that have been in the news lately that I want to talk about, and one involves objects that are about as far away as you can see. In fact, if you look at this image, is the image of what's called a quasar, which is one of the brightest objects in the universe. We can see quasars across the whole universe. They shine with brightness far exceeding the brightness of galaxies. What are quasars? We have every reason to believe that quasars are supermassive black holes at the center of galaxies. They're so bright because they're gobbling up so much material in the galaxy that as the material falls in, it emits lots of light. Now, the amazing thing about quasars is we can see them as far as we can see. In fact, we can see quasars that were formed and existed less than 800 million years after the Big Bang. That's an incredibly short time in cosmic terms because it took at least that long for galaxies to form. And there's a big puzzle, a chicken and egg puzzle, which we still don't know the answer to today. Which formed first, the galaxies or the black holes? Did galaxies form stars that would later collapse after they exhausted their nuclear fuel into black holes, which would then coalesce, later on producing a big black hole? Were black holes necessary for the galaxies to coalesce around them? We really don't have the answer to that question. But there's been a recent study that's shed some possible new light on this, and it's kind of interesting. In the early universe, when an early quasar formed, the earliest quasars, there were no stars around. And stars produce heavy elements. In the original universe, the only element around was hydrogen and a little bit of helium. But not heavier elements. All the elements that make you and I up, the iron, the nitrogen, the oxygen, were made in the cores of stars. Now, if I take a large gas cloud that might have collapsed to form a galaxy, it turns out, if there are no heavy elements, that gas cloud can collapse uniformly and might be able to collapse directly into a supermassive black hole before stars formed. And recently, a series of researchers have done simulations on computers, and they argue that supermassive black holes that form quasars might have been able to literally form from the first primordial gas clouds that collapsed in just a few 100 million years, before stars formed. In that case, the black holes formed before the stars. This work is very preliminary, but it illustrates this fundamental puzzle, and what's interesting about it is that it's necessary for us to ultimately determine our own existence. Did these black holes, supermassive black holes that formed, were they necessary for the galaxies to have the properties they have, ultimately, like our Milky Way galaxy, which has a supermassive black hole in its center, and ultimately for stars to form and planets and life like us? So this important fundamental question is an outstanding question. Theoretically, we've just in the last few weeks got some new information, which is preliminary, but the important thing is physics is an empirical science. And we will be studying this question with the new James Webb Space Telescope. That telescope will be able to look out to the earliest galaxies that formed, the so-called first light, when the first stars turned on in the universe. And it will help us understand that very chicken and egg question of black holes versus galaxies, and maybe resolve this fundamental question in cosmology. Now, the next mystery doesn't start out as a mystery. It still involves a cosmic object, and it involves perhaps one of the most famous pictures that's ever been taken in astronomy, if we look at it. Everyone's seen this. It was on the news earlier this year. This is the first image of a black hole. It's a black hole that's 6.5 billion times the mass of the sun, located in a galaxy 55 million light years away, the galaxy M87. And it's amazing that we can form an image of this object because the size of the object is smaller than the size of a solar system. How can we see that object 55 million light years away? Well, an incredible amount of human ingenuity. Astronomers combined the images from 8 different telescopes all around the Earth to effectively produce a telescope whose size is the size of the Earth. It was called the Event Horizon Telescope because black holes have an event horizon, namely inside of which nothing can escape. And what this telescope was designed to do was image a distant black hole well enough to hopefully see the difference between the region outside of a black hole, which is light, and the region inside of a black hole, which is dark. And of course, in this image, this is exactly what you're seeing. You're seeing the central image, which is presumably the black hole in the center, and you're seeing an incredible what looks like a disk of light around it. That's material that's swirling around the black hole, falling into it and emitting light. One of the things about this image that you see is it's brighter on one side than another, and that's also understood. If the black hole is spinning, we'd expect to see the light on one side be brighter that's coming towards us than the other. So this is an amazing image, and it confirms what we thought was out there. But sometimes science is more interesting if it doesn't confirm what we thought was out there. So you might say, well, it's unfortunate that this is exactly more or less what we predicted. It is, and it's nevertheless amazing, but scientists recently have suggested that maybe even this image, which looks just like it's supposed to, might give us information about things that we don't fully understand. For example, we know that dark matter, material that doesn't shine, dominates the massive galaxies, and one of the biggest mysteries in science is, what is that dark matter made of? I've spent most of my scientific career trying to figure out what it might be made of, theoretically proposing models and proposing experiments to look for it. Dark matter particles candidates are all over the map. Some of them are much heavier than the mass of neutrons and protons, some are much lighter. There's a kind of dark matter that's extremely light that's been proposed. It's called fuzzy dark matter. And for various reasons, it's billions of times lighter than the lightest particle we know of in nature, the electron. And if such particles exist, you can show that outside of black holes, there could be kind of a halo of these particles, a halo of this fuzzy dark matter. Now, what would happen as the black hole spins around? It would have impact in these particles, and it would cause some of them to be emitted in one direction more preferentially than another. And what that would do would be to slow down the rotation rate of a black hole. So the fact that we can see that the black hole like this is rotating already puts constraints on fuzzy dark matter. Because if the fuzzy dark matter was there of a certain mass, it would have already slowed this black hole down enough that it wouldn't be rotating. Now again, this is preliminary because the calculations are incredibly difficult, and we don't know exactly the rate at which fuzzy dark matter might slow the rotation rate of black holes. But I find it amazing that this image, which really was produced exactly what we expected to see, might nevertheless constrain material we don't understand. And it's possible that future images like this might actually, by measuring the rotation rate of many black holes, be able to potentially detect such fuzzy dark matter if it's there, or completely rule it out. So this image, which is really a testament to human ingenuity, can also provide us new information on the universe. I find it amazing. Now, I want to go next to not a mystery, but something that, for me at least, gives me pause. It reminds me how far we've come in science. This is an image of the entire sky. It's kind of distorted. There's the disk of our galaxy in that U shape. And that's all 360 degrees of the sky, and it's kind of a projected map of all 360 degrees, just like when you project a map of the Earth, you see Greenland distorted compared to the other rest of the continents, for example. But this is a map of the entire sky, and you'll notice the year 1991. In 1991, we knew of what were then 9 planets, the 9 planets in our solar system, and that was it. We had every reason to believe there were more planets in the universe, but they were theoretical and not observational. I had already received my PhD. I was already a professor at a university. We still didn't know of any planets outside our own solar system. But observers had incredible ingenuity, and in less than 30 years, this movie that I'm about to play shows you what's happened. So let's start playing the movie. Already by 1992, we discovered 2 planets, and if you look at this carefully, you'll see new little dots begin to form, and you'll hear them form as the planets are discovered in each year. By 1997, we'd already had a little more than 10. You can see these dots begin to populate this region. Slowly but surely, we were learning new ways to discover planets. The ways we use were remarkable. Looking at the wobble of a star as a planet goes around it was the first way we were able to essentially be able to discover planets. But then we were able to look at how a star gets dimmed as planets go in front of it. There were other techniques, so-called microlensing. All these new techniques began to come into play, and already less than 7 years ago, we had 700 planets around our outside of our solar system we began to discover. But then we created a satellite to just look at those planets, and look what exploded. By 2017, over 3,000, and just this last week, we hit a milestone. We discovered over 4,000 planets. And I find it remarkable to sit back and realize that less than 30 years ago, we knew of no planets outside our solar system. And now we know of 4,000 planets. Maybe some of those planets are habitable. Maybe there's life on those planets. We don't know. The rate has continued to explode as we send out new satellites to look for those planets, image them, maybe see the atmospheres of those planets, and maybe find evidence for life. Science progresses at a tremendous rate, and it's very sobering for me to realize that all the way up to my PhD and beyond, we knew of no planets outside our solar system, and how much has happened since then. we're learning new things about the universe at an exponential rate. The final news item I want to talk about is kind of old lang syne. It's about a device that I love, the Voyager 2 spacecraft. And here's a schematic of the Voyager 2 spacecraft. It's the object that's gone the furthest of any object that humans have ever sent out. The Voyager spacecraft is now over 11 billion miles from Earth. Outside of our solar system, it's the first object that's created by humans that's left our solar system, and it will continue to move throughout the universe, throughout our galaxy, for as long as it lasts. But what's remarkable is it was launched over 42 years ago, and it's still working. The engineers at the Jet Propulsion Lab are extremely ingenious. This is an object, a device that was designed to last for maybe a decade. 42 years later, it's still working in the cold, dark depths of space. In order to make sure this instrument, which has 5 different scientific instruments on it, continues to work, we first of all have to be able to communicate with it. That means its antenna has to point towards the Earth. In order to do that, we have to send signals to the spacecraft to make sure its antenna points towards the Earth, and it has little altitude thrusters on it that will continue to allow it to point towards the Earth. Those altitude thrusters have begun to stop working. But there are other thrusters on the spacecraft that were designed to adjust its trajectory as it went through the solar system. The last time those thrusters were used was 39 years ago. Just these past few weeks, engineers at the Jet Propulsion Lab turned on those trajectory thrusters, and they worked, and they were allowed to keep that antenna pointing towards the Earth. Now, there's a big challenge with this spacecraft. It's cold out there, and if the nozzles of the thrusters freeze, they'll stop working and we'll lose contact with the spacecraft. There's heat being generated on the spacecraft the same way energy is. There's energy being generated here to run these instruments by the decay of a radioactive nucleus, plutonium-238. It generates heat and power. And it's enough to power the instruments, but the plutonium is decaying, and there's 40% less energy now than there was, and the environment is much harsher. So what the engineers have had to do is adjust certain things and turn off the heat to certain of these experiments to keep the heat with the thrusters. And most recently, they've turned off the energy to something called the cosmic ray subsystem, which you can see as a white dot there. To measure cosmic rays, it's one of the ways we learned that the spacecraft was actually outside of our solar system for the first time. The heat to that was turned off. That device has now gone to over 74 degrees below 0 Fahrenheit. What's remarkable is it was designed to work to maybe 49 degrees below 0 Fahrenheit. Even though there's no heat at that device, it's still working. 42 years later, this device is still ticking. A triumph of human ingenuity. And so I want to just end these segments today talking about how amazing the universe is, but also this gives a testament to the ingenuity of human beings and the devices we create. This object will go out through the galaxy. It'll be the first thing that's potentially ever discovered by aliens if they're ever out there. It won't be working then. But the fact that it's continuing to function now is amazing, and it shows how much we can do with so little if we continue to try to explore the universe. Science matters. It's extremely exciting, and I was really happy to talk about these things today. See you next time.